Hi, folks, and welcome back to another lesson about the BCIT Technology Teacher Education 5060 Boombot version 2 project. And today we're going to take a look at getting your Neopixel strip right on here, or more correctly, your WS2812b strip to behave and have it so that it interacts with some of the controls that you're running back over here. So you should have your Wi-Fi control from your phone up and running, and your phone right now should be using the RemoteXY to talk to your ESP8266 chip right here, and your ESP8266 chip will be sending serial data over to your Arduino, and your Arduino will be then controlling the robot. And so that was our previous step, and you can see it's working right here. I've got the motors turned off at the moment, but you can see as I move the joystick around on my phone right here, I'm controlling things. Now, while we're working with the WS2812b strip, or Neopixels as they're called on Adafruit. They got a great trade name in for them. These are super bright little LEDs, and so sometimes I'll just put a piece of tape over top of them, and that makes them somewhat less blinding to look at. And you can see that as I move my joystick around, I've got all sorts of interesting information appearing down there. And as I play with my edge detectors, I also have LEDs changing colors and providing feedback. So right now I've got motor feedback and LED feedback happening in there. But as you can see, I've got some oscilloscope probes set up in here because this did not come easily. I know when I put these videos together, I pack a lot of information into 1 hour and it looks like I know what I'm talking about. But that's because I spent 8 hours the other day trying to figure out, why doesn't this work? So if you're ever wondering about this, it's because I pulled it all out on Sunday. Okay, the good news is I think I've got a solution that's going to explain to you both why it didn't work for me and why it will work for you. So let's get into it. Okay, so we've just swapped screens around a little bit here so we can take a look at the schematic of our board. And here is our Arduino right here. And on our Arduino, we've got the WS2812b strip can hook in to 2 different connections right here. And we're using one of them with the strip that we've got tied on right here. And you can see we're hooked into the one called H5, which is designed for working with the strips that I've got. But there's another standard format for hooking up to the WS2812b strips. So if you wanted to have a Neopixel ring or something else somewhere on your robot, there is another header H4 on here that uses the same pinout as the standard Adafruit or LED strip type of thing. So you can add underglow to your robot, you can add a whole bunch of different things, and you can tie it in right here. Just a couple of different ways to hook up to it. We're using this one right here. Our data for this is going to come out right here on pin 10. It goes through a resistor because it is just data, and it comes out right here, and our data flows in from one end right here. Now, it's important to remember that the way the WS2812b strips work is that they're each a 24-bit color. So there's 8 bits of red data, 8 bits of green data, and 8 bits of blue data. And so to tell this LED what color we want it to be, and let me just change its color right there by controlling it. To change that color, what we do is we change the data that flows to it, because there is a microchip right on that WS2812b chip. If you look really carefully at it when the light's off, you might even see the microchip in there. And that microchip controls the PWM signal to 3 different LEDs on there, a red, green, and a blue. There's some fancy ones out there that have a 4th white LED built into them now. That's going to take 4 bytes of data coming down the line. So each one of these in our setup needs 24 bits of information. And so what will happen is we'll send data down the line, and the first 24 bits will get eaten up by this LED right here. And then the next 24 bits will get eaten up here. So by the time we're all done, we need to send 24 bits times 8 LEDs to give all the signal information on here. And that's all going to flow out of a pin on our PIC, in this case, on our Arduino, in this case, pin 10, that's going to be turning on and off super duper quickly. And I'm going to talk about that because the speed that we've got to turn it off to talk to these chips is going to create some problems for us. And thankfully, there is a solution for it. Now, the other thing that these uh, Pixels need is a stable power supply. They do suck a lot of juice if you turn them on to full brightness. So don't turn them on all full white, okay? It'll be really bright and it'll suck about half of an amp. I'll talk about that and why that's not a great thing for your circuit a little later on. But we do have a capacitor right here just to smooth things out and make sure that they have a stable supply. Now, the other thing that we have going on is that we have our phone control right down here. And our phone control is coming in, as we said, from our ESP8266 down here. And this is also a serial data stream of bits. So in other words, a set of pulses coming in, turned on and off rapidly. And we have our Arduino talking back and forth here. So we actually have two lines. We have our Arduino transmitting, okay? And so our Arduino comes down here and transmits data to our ESP8266. And our ESP8266 also sends data back to the Arduino along the RX line coming in right here on pin 0. And this is where we started to run into some problems because this data was coming in so rapidly while we had other data going out so rapidly that there was just a little too much for our Arduino to do. And you've sometimes heard me talk about how the fact that the Arduino is not a particularly powerful microcontroller in terms of processing power, only runs at 16 megahertz. This is one of the very first times I've actually ran up against limits of what the Arduino can do and ended up wishing we had a more powerful controller. You're going to run into the same problem if you're using a Bluetooth serial module right here, although as you'll see, if the Bluetooth serial module is running at a lower data rate, you might not have the problem. In fact, we're going to solve our problem by actually slowing down the data rate from our ESP8266. But before we get there, I want to show you a few other neat things that we can do with our Arduino IDE and just take a quick look and review some of the software. Okay, this is the wireless drive setup that I have for my Boombot, and this is what's got the control running right in here. So hopefully before you get to this stage, you've got this set up and running on your Arduino. Okay, now one of the things that you'll notice as we start to get in here is that our code starts to drag on and become really, really long. And when we're looking for something in here, it's hard to find because the code just keeps on going. And quite frankly, it's going to get longer as we add more things. So thankfully, there is a way to break this down and make it a little easier to read. Okay, and what we're going to do is we're going to come in here and right up here on this blue part, if you come over to this corner, oops, it's behind the screen. Let me just minimize this a bit so you can see it better. And what we've got coming in here is you see this little drop down arrow over on this corner of your screen. If you drop down on that, and of course that disappears behind me. If you drop down on that, you'll see that it says New Tab, okay? And click on New Tab, and down at the bottom here, it will ask you to name that new file. And I'm just going to call this drive, okay? Because as you know, we've got a drive function and it takes up some space. So I'm just going to type in drive right in here. And now you'll see I've got my main code section right here and a drive tab has suddenly appeared right on here. This is nice. Let's come down here and find our drive routine. Okay, and where does our drive routine begin? This is our drive routine. Make sure you get everything, including those first slashes of the comments in there, and write down until we're done with our drive routine. And copy that. Actually, sorry, cut it. Cut it. We want to get that out of there and put it right into here, into your drive routine. Paste it in right there. Okay. And now just to make sure that worked properly, do a quick check, let it compile the sketch. It's done compiling. And now when we look at our Boombot code, now we've moved some of that material out of here so that when I come down here, I've got my loop, and that's the end right there. I don't have all this drive function right in here. I can package this up, put it off in a different tab, and it makes it a little easier to see what's going on. Now, the other neat thing about that is if I save this file, and I'm just going to save it with a slightly different name. I'm going to save this as, let's see, this was my 006C. This is going to be my 006D wireless joystick drive with tabs. You can call it whatever makes sense on your system. Okay, and oh, that just saved the drive part. You can save them all independently now. Oh yeah, no, there we go. That saved everything right on there. And if you come in and take a look at that on your computer, this is, let's see, in my Dropbox, electronics, Boombot 2, it's in the code section, so I got to keep everything laid out here. 006D, wireless joystick drive with tabs. And now you'll see that it actually breaks it down into multiple segments of code. So this actually makes a bit of a deal because when you upload your code down to show me what you've done or to ask for someone with troubleshooting assistance, you do have to make sure that you include both of these units of code in here because you've broken your code into two pieces that are put together. In a way, you're starting to make your own libraries and you've moved your programming sophistication up a level. And this is kind of cool because what you could do if you had multiple people working on a team to solve a robotics programming project, kind of like if you were running a high school robotics team, you could break the coding down into separate modules, and one student could be responsible for getting one section up and running and talking to the other section. Then you can bring them all together. And that's a neat way to make things work. So let's come back to our Arduino code right here. And there may be other sections that you want to pop off into here into your tab. Now it's good if you kind of do it in logical chunks so that if you wanted to have your setup code set off in there somewhere, you could have a setup tab. And quite commonly we'll have all of our definitions and declarations because you can see they go on for quite a long way. You can have them all set up in a tab. So I'll let you set up your tabs in the way that you want them. But it's nice to be able to have those tabs and have those chunks and break your code down so that you don't have 30 screens of code all punched together. What's nice is that when you've got a section of code that works reliably, you can put it into a tab of its own and don't mess with it. Okay? If it's not broke, don't fix it. Okay, so this code's running along really nicely here, and we want to start adding some Neopixel functions to it. So before we go doing something fancy and trying to bunch a whole bunch of different things together, let's just make sure that the Neopixels work. Now on mine, you can see that they do, but we want to test them on yours, and we don't want to test them with a bunch of complex code that's messing you up. Okay, we want to do this so it comes out in a sensible way. And so let's just test the Neopixel LEDs. Now, there's a couple of very common libraries that allow you to use the Neopixels. And the libraries, for reasons I'll talk about in a bit, actually do some pretty magical things. And I've got the both libraries installed on my system. And let's see, you should have under your examples, if you've got them installed, you may have used them already. You might see the Adafruit Neopixel library. Okay, so if you go Files, Examples, you can take a look down there. Now, don't panic if you don't see it. Okay, you might also see the Fast LED library. Both of them are excellent libraries. The Fast LED has slightly more advanced coding. It's a newer library that was designed to address some of the things that Adafruit Neopixel didn't do so well. But the Adafruit Neopixel library has an amazing tutorial on Adafruit's site, and both of them work perfectly fine with this. So as we do this, I'm going to use the Fast LED library, but if you're a fan of Adafruit Neopixel, thumbs up to Adafruit, and you'll be able to use Adafruit Neopixel with this just as easily. Now, if you don't have either of those libraries, remember that it's easy to install a library in the Arduino IDE. Tools, Manage Libraries, okay, and a window will pop up on here, And you can just type in our case, fast LED, and it will search through there. And you can see where did that go? I've got the fast LED library version 316 by Daniel Garcia. Thank you, Daniel, installed. And you can select various versions and update and all that. Works great. You don't need the Neo Matrix or anything like that. There's more variants of fast LED out there. Oh, I don't like using the word variants in the spring of 2021. But anyways, there's more of the variations of the fast LED library available. We just want fast LED, Daniel Garcia. I've got version 316. There might be a new version out there by the time you come along to do this. If you prefer the Neopixel library, it's the Adafruit Neopixel library. And not the DMA library, not the just the standard Adafruit Neopixel by Adafruit. And you can see I've got version 1.7 installed. Okay, so go out there and get the fast LED library for the purposes of this video. But if you're a big Adafruit Neopixel library fan, just do everything I do, but with that library. Okay, so let's come along here. And now that you've got the library installed, you should be able to come down here and you should be able to see that Fast LED has some examples on here. And let's just pick one that's pretty simple to start with. And the Cylon one is pretty cool. Let's bring that code up right in here. And so this is written for the Fast LED library. And if you were able to pull that up as an example, you probably got your library successfully installed on the system, but let's test it out anyway. Now, we've only got 8 LEDs in here. So let's set that to 8. And our data pin is going to be on, I think I said pin 10. Now it's written right on the board. You can double check. It's kind of tucked away underneath a capacitor right over here. But I tried to make sure that the board helped you out all the way along. I wasn't so helpful when I stuffed all the information underneath the Arduino there, but where else was I going to put it? Okay, the clock pin doesn't really matter because the WS2812b Neopixel chips are what we call asynchronous serial. Okay, in other words, A for not and synchronous timed. Okay, a synchronous serial port is where you've got one line providing a clock or a rhythm or a metronome that controls the flow of data, and then you've got a data pin. Okay, there's my clock pin. It's like rubbing my stomach and patting my head at the same time. Data pin coming along down here, or sorry, clock pin, just a steady rhythmic beat. And then you've got a data pin that will send a 1 or a 0 or a 1 or a 0 or a 1. And so those two will work together and you'll need 2 lines to transmit the data. Now the nice thing about that is that the timing isn't so precise. But in an asynchronous system, everything has to be particular, bang, bang, bang on an exact time period. And so if we'd used a synchronous system with a timing line on there, a lot of the problems that we're having right now would have gone away. But because we've got particular timing, we don't need to use a second pin, so you don't need to worry about which pin is the clock pin. You just need to make it run. Okay, now, just walking through this file so that we understand what's important in here. When you've installed the library, it creates an object type called LEDs. Okay. Now this object, we could use a different name. I think in my code, I'm going to use the name pixels, but you could call it Bob right here if you wanted to. Okay. And it's just going to take the number of LEDs that we defined right up here at the beginning. And it's going to set up this object so that the object knows, hey, I've got a strip with 8 LEDs in it. Doesn't know that it's a strip. It could be rings. It could be individual LEDs. Okay. This is just some information where it's going to talk to your computer. For some reason, it chose 57K BPS. We are going to talk about baud rates on the serial port in a little bit. So that sometimes matters. And then it resets things. And now it goes in and it uses this LEDs function. And it comes along and it adds some LEDs of the WS2812b, because this actually works with different types of LED strips, it puts them on data pin, and it says they're an RGB mode, and it passes the data of this color right here and the number of LEDs down there. It sets their brightness, and then it goes and it runs some things right on there. And if we upload that code, you should see fancy colors fading back and forth on there. Let me put that piece of tape back over top of here, and you can see that now I've lost my wireless connection. That's okay. Ooh, that's still really bright and hard to see on there. If that's not bright enough for you, let me dim that. I'm just going to change the maximum brightness so that you might actually be able to have a chance to see that go on the camera. But it should be looking good on your robot right about now. Now, if that's not working, stop here, because you've got a problem with the LEDs. Okay? Can you actually see that fading in and out a little bit now? There we go. We've got some different colors going along right there. Sometimes that's just too bright for my poor little camera. Okay, so stop right now. If you can't get fast LED to run the Cylon sketch, or let's try something even simpler out of here, examples and fast LED library, and come in here and let's take the blink, okay? And you can just put it on there. Remember that you need to set this up with the number of LEDs you want to change. You can put 8 on there. Our data pin is 10. And if you change those two things, it'll upload. Oh, this one's only changing the one LED for me, but that's perfectly fine. That means we have communication. Okay, so make sure that completely separate, this has no drive code or anything in it, that your LEDs actually work before you start trying to integrate things. Okay, if that's working, great. Let's move on to the next step. Now, before we get to the next step, I have to dig into some technical information. So let me move the robot out of the way. And just around the corner here on my desk, somewhere over that way, I've got a nice little Tektronix scope. And that's really useful because it helped me a lot with the troubleshooting that I was doing right here. And I think I'm going to bring this up as the bigger screen again. So just hang in there. Okay, there we go. And so this is, I'll just ignore this part for right down here, where I started to run into some interesting problems with this board. Okay, now this is our Neopixel data stream right here. Now the Neopixel library, the fast LED library, they both do the same thing. Like I say, they have some very specific timing requirements about sending their pulses down here. So this is just an oscilloscope trace. We've got low right here, which is in our case we'll call 0 volts, and we've got high, which we call 5 volts. And to send a signal to the Neopixels, it's going to turn a pin on and off exceptionally fast. Now, it's not exceptionally fast for a more powerful microcontroller, but for your little 16 megahertz Arduino Uno, it's flying to try and send this because each of these 24 bits has, each of these bits is controlled by the timing of a single individual pulse right down here. And those pulses basically have to be accurate to a couple of nanoseconds, a couple of billionths of a second. And on the Arduino, that works out to just a couple of clock cycles. Okay, now by a clock cycle, I mean how long it takes for the processor to complete its simplest possible operation. And the timing of this has to be accurate to just about 3 of those minuscule clock cycles. When you do a digital write, which seems instantaneous to a human, Take a look at it on a precision oscilloscope sometime. Your DP scope's probably not quite enough to do it, but take a look at a good precision oscilloscope on how long it takes you to turn an LED on and turn it on and off in an Arduino if you use digital write high and then digital write low, and it will actually take longer than it takes the Neopixel library to send many bytes of data. Now, the reason that the library is able to do this is because it seizes complete control of the microcontroller while it's doing this. It does something called turning all the interrupts off. You'll recall we talked about interrupts when we were doing the encoder reading. Well, there's a whole bunch of interrupts happening on your Arduino that until you read the data sheet and get a little bit more into it, you're probably not that aware of. One of those interrupts involves serial data communication. And we just spent some time talking about serial data communication because we're using a serial connection, a hardware serial connection, to get data from our ESP8266 to our Arduino. Okay, so what happens when we do that is in this section, we've got all the interrupts turned off. I should spell that correctly. Just for this little section right in here, while the fast LED library or the Neopixel library seizes control, this is like a total of, in our case, 250 microseconds out of about 100 milliseconds. So this would take place, I've got set up so that this only happens about 10 times per second, okay? And it's only for 250 millionths of a second when it happens. But during that period, the Arduino can't perform any other functions. All it can do is send this data. And that means that you run into a little bit of a problem because we can't control the when the ESP8266, so this is our ESP8266 data, this data is flowing in to the Arduino, and it's coming in with a whole bunch of on-off pulses as well. Now, I've intentionally set your board up so that we use the hardware serial port. That's why it was really important that we hook up the ESP8266 to pins 0 and 1. Even though sometimes 0 and 1 clash with programming your Arduino. So you'll remember that when we set this up and we talked about the ESP8266, we talked about the importance of this CHPD enable pin and how we use a pin on the Arduino to turn this LED on, which activates the ESP8266. Okay, now that's important that we can do that because when it comes time to program your Arduino, you need this connection to shut up and disappear. Well, the cool thing about what the Arduino does is when you send a command to reprogram the Arduino, the first thing it does is it turns all of the outputs off, which means it turns CHPD enable off because that's just controlled by a pin on your Arduino, which effectively turns your ESP8266 off. So this no longer holds pins 0 and 1 of your digital hostage, okay, so that you're able to upload code onto your Arduino. The catch is we can't just go and turn that on and off while we're uploading data to our Neopixel, because if we do that, this takes too long to boot back up again, and we'd have horrible latency in our remote control drive. Anyway, we've got data coming in here, and because we don't have any type of hardware flow control in here, we don't even have software flow control, and if you get into serial communications, you'll learn that flow control is basically like having an extra line of data on, an extra line running along saying, okay, I've got my headphones on now, I'm ready to listen what you've got to say. This thing just talks, whether we're ready for it or not. And that creates a problem, because although the Arduino has a hardware buffer that can store this data as it comes in, it can only store 1 byte of it. After it stores 1 byte in the hardware buffer, it raises an interrupt flag. And it says, hey, I've got 1 byte of data in my hardware buffer. I need the CPU to come in and put it somewhere. If that flag goes up in this period right in here, okay, the interrupts are turned off. Now, this doesn't always happen, but it happens often enough when we're sending that data, that what happens is that you end up with that interrupt not being handled because the interrupts are turned off. It doesn't get handled until over here. And you end up losing these bits of data that are coming from your ESP8266. Now, the remarkable and resilient thing about the Wi-Fi communications that we're using and the protocol that's in place for running the RemoteXY is that that doesn't crash the system. It creates an error because data is missing from a packet. And the RemoteXY software says, I heard something wrong. Dude, it's totally messed up. You've got to retransmit that packet. Now, while it's saying you've got to retransmit that packet, we may have had another Neopixel pulse come right in here and jam that bit of data so that it might take 3 or 4 tries for it to say, okay, you've got to send me a packet, and then 3 or 4 tries for a good packet of data to get through. So if you try to run this with your Wi-Fi at 115 kbps, you end up having these glitches that don't crash everything. They just massively increase your latency, the time it takes from when you give a command on your phone for that command to be activated on the Arduino. I was getting latency almost up to 1 second sometimes. So I'd tell the robot to turn left and it would sit there and hum-haw around, and then it would finally turn left. Now, that's actually pretty cool if you're trying to simulate driving a robot on the moon, because there's a couple seconds of latency. Actually, I think it's about 1 second of latency between here and the moon. Or if you're simulating driving something on Mars, where we've got, 8 minutes to get a signal to Mars and 8 minutes to get the signal back from Mars. So really, driving robots on other planets, it can be done. You just need to be very, very patient and not expect a very quick response. Driving it in your living room, we should probably be able to get a little better latency than that. So we needed to come up with a solution before we could start writing too much code and making it work. And I tried all sorts of different things. Somewhere through, I'd say about 4 hours into the problem solving process, I realized that, the easy solution is probably just to take this data and slow it all down so that we never have 1 byte of data arrive during this time. Because if it takes longer than 250 microseconds to receive 1 byte of data, then our interrupt flag, our hardware interrupt flag, will never trigger during this period where the interrupts are off. And if it does, well, we probably won't lose that much data anyway. So we do have a way to do that. We just have to slow down the data transmission from the ESP8266 to the Arduino. And we need to change our code in 2 places to do that. The first thing we have to do is we have to change the default setting on the ESP8266. Now, for students in my class who have access to the Desire to Learn repository of code for this, you will find a program available in there called Boombot V2 6A Reset ESP8266 baud rate. It should be in the same folder that we introduced the Wi-Fi communications and the RemoteXY. And I put it in there because sometimes our ESP8266s come to us with different baud rates built into them. And we don't know what the baud rate is, but we want to change it to some default value. The default value that most ESP8266s come with is 115.2 kbps, or 115,200 bits per second, and that's what we've been running at so far. Okay, it's a great baud width or baud rate for connecting from this controller to right here using the hardware serial port. It's a little too fast for the software serial port, but it works great. We can slow it down pretty easily. So this code right here, and it's pretty simple code. So if you don't have access to the uh, D2L folder, I've left it on the screen here for a bit, and you can press pause and feel free to copy it right away. Um, basically, this works for our Boombot. If you're using an ESP8266 in a different situation, you might need to configure it. So we come in here and we turn our CHPD enable on. Okay, that wakes up the ESP8266. We give it 1 second for it to wake up. And then we come in here and I actually could have put this in the setup routine. We only do it once. We're just going to go through here and we're going to try 11 standard baud rates. Okay, so we don't know what baud rate our ESP8266 is at. So we're going to start out slow and we're going to get faster and faster and faster as we go along. And so I've set it up to the standard baud rates of 300, 1200, 2400, 9600, etc. And we're probably going to actually finally get communication at 115,200 bits per second, but it'll try them all. And so it's just going to loop around here 11 times, and each time it does it, it's going to look into this array and pull out a different baud rate, and it's going to send a speed up here. And in my code that's up on D2L, I'm resetting everything to 115,000. Okay, so you are going to have to change that 115,200 number right here to 9,600 bits per second. The other data in here is 8 bits per byte, okay, or 8 bits per character. Oh gosh, I'm forgetting what the rest of it. It's like parity bit, no flow control, and we can look that up in the ESP8266 manual and definitions. And what it does is it sends this command right here that looks really obscure, but actually kind of means something. AT, for those of you who remember the days of modems, you may remember when you had your modem go to dial a phone number for you so that you could connect over your telephone to the internet. Those were the days. Whee! If you remember that sound, you used an AT command. You used AT-DT plus the phone number. And that would, AT would wake up your modem and say, hey, this is a command coming in, DT, dial, and then you'd put the number on it. In here, what we're saying is AT, wake up and listen for a command. UART is Universal Asynchronous Receiver and Transmitter, which is the $50 way to say serial port. Wake up your serial port and change its default value. Okay, so UART def is your serial port default value, if we wanted to say it in English, and set it to 9,600 bits per second with all these other configurations in here that I have temporarily forgotten. Okay, and so that's going to send it down the line, and anyway, this will set it up, and this tests to see if it got set to 115,000. You can set this to 9,600 as well, and if it did get set up properly, you'll see a little website pop up called Boombot. You won't be able to do anything with it. Okay, it just creates a hotspot so that you can confirm that it worked. And then it just comes down right here, and for basically forever, a while one loop is an endless loop, it will just keep sitting there poking this saying, hey, I'm an Arduino, I'm here, I'm here, I'm here. Anyway, so if you upload that code and run it once on your Boombot, okay, that should come in here and that should turn on your ESP8266. You should see the CHPD enable go high, and now you should have changed the default settings on your ESP8266 to 9,600 bits per second. If you ever need to change it back to 115,200, just come in here and change this code right in here. This is designed specifically to work with this board. Okay, and there we go. So before you go too much further, get that changed and make sure it works. Okay, and then come back to your, let me get rid of that for a minute. Come back to your wireless joystick drive. Okay, and now get this working, because you'll remember in your wireless joystick drive at the beginning where we were setting up our RemoteXY, we told it to set the speed to 115,200 bits per second. Slow it down to 9,600 bits per second right in here and upload that code. Okay, and now that should boot up and it should work exactly as it did before. So you should be able to come in and take your phone and make sure you're connected to the right hotspot. My phone always defaults back to my home network. And now you should be able to pull up RemoteXY and bang, there's my controls. And it looks like I've got control back on my Boombot, okay? Just now I'm running at 9,600 bits per second. And now that means that I should be able to send data down to here without blocking the bytes as they come in. Yeah, it's a little more complex than some of our initial setups, but if you've made it this far and you've got everything working at 9,600 bits per second, getting this set up should be relatively easy. Okay, so we've got this all running right in here. And now what we're going to do is we're going to take a look at, well, what do we need to add in here to get our Neopixels working? We've tested the Neopixels, we've adjusted our speed. Let's go in and start seeing what do we need to make this work. So we're going to come in here and let's see, we had that blink routine working. So I like to put these two screens kind of side by side like so and go through and identify the important parts that we need. Okay, so right in here, we've got our RemoteXY stuff, and let's just do this. You could either do all your includes right at the beginning, or you could include them chunk by chunk, or you could set up tabs for each of them. Okay, so you've got a number of different things that you can do for putting this together. I'm going to tuck my ESP, my fast LED code right in here after I've defined all of my RemoteXY stuff. So right after that pragma pack pop command, that's when pretty much everything in there is done. Now the first thing we have to do is we have to include fastled.h. So we'll just copy that over there. Now if you want to make this really easy to see, put a couple of slashes in here and a big line right along here and just type, okay. Oh, now because I've got slightly larger font so you can see what's going on, and because I'm splitting the screen up here, oh, because I'm splitting the screen up here, I've got all sorts of excitement happening. Okay, I don't need that screen. I do need that screen. There we go. This one just happens to be stretched over onto my other screen and it was annoying me, even though you couldn't see why it was annoying me. Okay. So there we go. Screens are set up. Uh, we've got include fastled.h right in here. Okay. And then we need to define our number of LEDs. So let's just copy that right out of there. Okay, so we've got two definitions in there. We had our data pin defined as pin 10. So we can take that right out of there and we can drop that right in there. And then we need this command to define the arrays. So that's where it's going to store all of the color information before it gets ready to, it gets ready to transmit it. You can see that this is designed to work with a whole bunch of different types of LED strips. Well, the one that we want is the Neopixel, as it calls it right in here. You can see this is the only one out of this that's uncommented. And you'll also notice that this section is now in the setup routine right in here. So this is in void setup. So these are our definitions in right here. So we can say, okay, we're done with that as far as definitions go. And let's come down here to void setup. Okay, so in our void setup routine, now we can add this line right here. Okay, and I really like this style of programming. Always take a moment before you get too deep into it to just do a check and make sure you're not generating new errors as you go along. It's easier to solve one error at a time than to solve a whole bunch of them. Okay, and then down in our loops right here, okay, looks like we're ready to go. We've got fast LEDs, Neopixel, it's got the unit up there and running. It knows which pin we're on, and it knows how many LEDs there are and which array should be controlling that. Okay, so let's just do a little test right down in here. And before we even call RemoteXY handler, we're just going to do a quick little test in right here. And we're going to copy this code, just those two lines. We'll get rid of them later on, but I just want to do a test and make sure that this is working okay. We're going to set the 0 element of the array to red, and then we're going to say fast LED.show. Let's just upload that to our Arduino. And hey, that first LED came on. Okay, so I think we're starting to get something figured out here. All right, fast LED show is necessary to take the data from this array of LEDs and dump it out to right here. And it's while that fast LED shows that it is executing that we run into problems and have all the interrupt turned off. It's for this really tiny period of time, but it still happens. Okay, so now we've got this hooked together, and since this is also hooked together and running, and since this is running with your robot drive code, take your phone again and check and make sure at this point that you can connect. There should be a Boombot Wi-Fi network, and all your drive code should be working again. And just a minute. RemoteXY, connect to Boombot in there. And yeah, I've got those lights blinking and turning on there. So that means that I am going to be able to drive my robot around, and I have some form of control over those WS2812b strips. Okay, so we've got the hardware working. Now we want to make it do something interesting and useful. Let's just get this out of here for a moment. Okay, so we've got that working right in there. And what we're going to do is we're going to come down here, and at the bottom of our code right in here, we're going to create a new function. Now, I'm going to create that new function before I start going off and putting it in a new tab, okay? So I just want to make sure everything works before we let the tabs start making anything too complex. So I'm just going to use that line right there to delineate things. It means nothing to the program, but it makes it easier for me to see where I'm looking. And right down at the bottom here, I'm going to create a new function called void, and we're calling these LEDs in here. So I'm going to call it void update LEDs and bracket, bracket, big squiggly bracket, and some space in here and a closing squiggly bracket. Okay, now, as you'll recall from creating other functions, void means this is not going to return any data. Okay, we created the range finder and we said int range finder, bracket, bracket, okay, and what we meant on there was that the range finder function returned a value, or returned the range as an integer. This one's just going to do a bunch of commands and it's not returning anything for us, okay? And we're also not passing any data to it because our variables that we're going to use in here are already established as global variables, and every function in the program can see them. Okay, you'll sometimes run into an error not defined in this scope, and what that means is that maybe you're not using a global variable, which is actually a good thing in many cases, but it means that within your scope, our scope right here being between here and here, unless we define a variable inside here or a term inside here, or unless it's a global variable that's available to the entire program, nobody's going to be, or this routine won't be able to see it. Okay, and now what we're going to do is let's just test this, because I like to test things little segments at a time. We knew these commands are good. Okay, let's copy them and let's put them in here. Okay, and now we'll put this in here and let's test our function, okay, by coming right up in here, and where was there's our setup, here's our loop, and right in here, right at the beginning, we can say update LEDs. Okay, so when it sees that, and let's try running that and make sure that everything comes through in red. Oh, what did I just do? Did I miss a squiggly bracket somewhere? So if I run into that not defined in the scope or not declared in the scope, I'll do an auto format sometimes, and it looks like Arduino helpfully inserted an extra squiggly bracket down here at the end for me, and that might be all that it was. There we go. That compiles on there. So I didn't actually mean to do that, but it tied in nice to get a not declined in the scope error, and sometimes they are fairly quick to fix. We've uploaded that code. That red is on there right there. And let's change this, and we can make this one blue, and let's do it for LED 1. There we go. Okay, so if you're able to do that, now you're getting control of this running right through here. Let's make a tab for our update LEDs function so it's easy to use. So come over here and new tab, and let's call that update LEDs. Okay, and then we can come right in here and let's just copy everything from update LEDs. Or let's cut it actually. We don't want it in two places. Make sure you got everything in there, okay? If you miss one character, as you're no doubt aware by now, your Arduino is going to have a hissy fit. And paste that into right there. And now anytime we need to find that update LEDs function, it's sitting right there in a tab. And let's verify that and make sure that we did it right and it compiles properly. Okay, we're actually getting into some pretty sophisticated stuff right here, which is why I've saved this until a little bit later on in the programming process. So what are we going to do now that we've got a way to update LEDs? Well, before I get to that, there is one more thing that I'd like to do. I'm able to watch this on my oscilloscope, And looking at that right now, I can see that we're running the update LEDs function and sending that pulse down to here. About once every, well, let's see right on there, about once every 2.5 milliseconds. Okay, so we're updating 2 milliseconds is 500 times a second. We don't need that level because we're updating every time we come around. I don't want to update my LEDs every time we come around. So I want to slow that down a little bit. Now, a common way that we do that is using a delay statement. And although we've been using delays extensively up until now, they're actually not that great programming process because they're what we call a blocking function, and none of the rest of your code gets to run while you're doing that. What we'd much rather do is we'd much rather have a little variable in here. Okay, and now I'm going to create what we call a local variable. Okay, the global variables are all defined right up at the top of the program. In this section here, those are the ones that we can access from anywhere. A local variable will be defined within a particular function. So if I define something right in here, only loop can see this variable. This is useful for what we call memory management, but also, as I was saying, when you break these various tabs up, where'd my mouse go? As you break these various tabs up across the top, you could separate these out so different programmers could work on different sections, and they could have their own variables and their own memory space dedicated to their function, and they don't have to worry about somebody else's variables and somebody else's functions messing around with the stuff inside their code. So it's a nice way to separate code down into smaller chunks is by working with local variables instead of global variables. Okay, so in here, what I'm going to do is I'm going to have an unsigned long variable called last LED update. Okay, and I am going to set that to whatever we read from the millis function. Oh, no, I don't want to do that there. I'm just going to, I'm not going to be able to set it up. I forgot that. Looking at my notes over here, and I'm like, don't set it up as local. It does need to be a global because we do need to be able to access it from setup right in here. So much for that great introduction. This is a place where we need to have it set up as a global variable. So come up before setup, unsigned long last LED update equals 0. Oh, it's not an underscore in there. It's just a space. Okay, so we use unsigned long because that's the big data format that the millis function uses, and this lets us keep track of time, okay? So this is going to remember the last time that the LEDs were updated, and we need to be able to set it up in here so that when the program starts, it knows that it equals 0, okay? And then down in our void loop program right in here, what we want to say is if millis minus last LED update is greater than 100, this will update our LEDs once every 100 milliseconds. And let me just make sure I've got my brackets all matched here. Oh, I need one more bracket in here. Okay, so that we can take a look at, the math. It does the math function, then it does the comparison function. And then we are going to do two things. So update LEDs, then we have to update our last LED update equals. Okay, so what comes along right here is when our program starts, last LED update is equal to 0. So until millis gets up to 100, okay, this function doesn't update and we don't update our LEDs, and we don't end up blocking any data coming into our Arduino. So this just keeps our LED update from hogging the processor. Okay, puts it on rations. You only get to run once every 100 milliseconds. You can probably set this down to every 50 milliseconds if you want it to run smoother, but it was running naturally at every 2.5 milliseconds, which is just faster than it needed. Okay, so it comes in here and it checks, and have we gone 100 milliseconds since the last LED update? If we have, go and update the LEDs, and also update the last time that the LEDs were updated. So keep track of, oh, now it's 101 milliseconds into the program. Don't do it again until we're 201 or 202 milliseconds into the program. Note that I don't use an equal right here because we don't know that we're going to hit that exactly on the point. We could say an equal to or greater than, but greater than's plenty good. Okay, so this means that every 100 milliseconds, we're going to call the update LEDs function, and the update LEDs function we've now got set up in a tab over here, and right now it's doing something fairly boring. Let me switch the screens around and show you what I want it to do just as a basic thing, and we'll let you take it from there. Okay, so it's good to have a plan before you get started, and rather than doing a funky Cylon display or anything in there, I wanted to be able to pull some useful data out and have a data display showing what's going on. So I laid out my LED strip right here, and what I want is pin 0 right here, sorry, LED 0, 1, 2, 3, 4, 5, 6, 7, because our data comes in from this side, and the first 24 bits go here, the next 24 bits, next 20, etc. So as that data goes along, it heads down there, and I want my left motor to indicate, my 0 LED to indicate what my left motor is doing. And if it's going, I don't know why I drew forward in that direction. But if it's going forward, I want it to be green. If it's going reverse, I want it to be red. And then I want it to be dimming and brightening as it goes forwards and backwards. Okay. Now, a couple of things that we do need to pay attention with the LED strip. I mentioned it earlier that each of these pixels can draw. If you set it full bright white, that one's going to draw 60 milliamps. Okay, that's 20 milliamps per each of the 3 LEDs in there. And if you turn them all on bright white, that's going to be 480 milliamps. Your typical computer USB output only has to be rated to 480 milliamps. A lot of them will put out up to 1,000 milliamps or 1 amp. But you have other things running on your board that you want to be able to power. And so I don't think you want to be running 480 milliamps through here. In fact, if you're paying for your own 9-volt batteries, you definitely don't want to be running 480 milliamps because this is all powered by your 9-volt, and it'll end up killing your 9-volt faster. So what we want to do is maybe we only want to run one color, or you want to blend the colors together, but we also don't necessarily need to run everything at full brightness. Full brightness on Neopixels is blinding. Okay, there's no need to run it at full brightness. In fact, what I find is that when you get past about 32 out of 255 on a given color, all of a sudden the brightness gradations start to become pretty difficult to distinguish with the eye. So, in here I was saying there's a function called set max brightness to this. All I'm going to do right in here is I'm going to say is that when I'm at 0, I'm off, and when I'm at full brightness, I'm going to call that 32. Not 255, okay? Because 255 is too bright. And in the other direction, I'm going to go 0 to 32 because 255 is too bright. And by too bright, it's also sucking additional current that you don't need to get the data out. Okay, so now what we want is we want to take away, and we're just going to work on one motor at a time, because if we get that worked, we can come over and we can take a look here. And then we can also use that data to take a look at how we can set our edge detectors up. And then you can do something funky in the middle. You can have it show what your encoders are reading, or whether you're firing your cannon. You can play around with colors. There is an RGB function in in RemoteXY, so you can actually use your thumb to control the colors these are at. So there's all sorts of neat things you can do with the remaining ones. Once I show you how to set up and update 4 LEDs, I'll leave the middle 4 up to you to figure out what you want to do with. Okay, so that's my plan. We're going to take a look at this one right now, and we're going to take a look at the code that can make that work. Oh, okay, I'm back. And I've changed up a little bit of code on the screen. This is still the window that we're working in here, writing our code. I've got my Update LEDs tab open, and it's nice and clean and easy to look at. And right now we just had some nonsense code in here to turn one of our LEDs on. And let's just delete that and put in something a little bit more useful. Now, I've had a chance to play around with this in advance, and so I'm just going to copy this line of code and paste it in right here so you can see what I'm doing. Well, that was vaguely frustrating, but thank goodness for the power of editing software. You won't see the part where I sat here and scratched my arm and looked blindly at the screen while I thought I was on pause. And we will be able to recreate the part where I was talking towards the screen about what I was supposed to be doing. Well, I thought I was not paused. So OBS Studio needs this big flashing pause button on it to let me know when I'm paused and when I'm not. So um, if it seems a bit disjointed, that's because it was an hour or so ago I was recording the video and talking about what we're going to put in here. So we're in our Updates LED tab, Update LEDs tab right here, and we've got the void Update LEDs routine running. And here we've got this command that we were taking a look at for getting our first LED to turn green if we're moving forward, okay? And so we take our left motor value that we're reading in from the virtual joystick on our phone, and then we run that through a mixing routine, and we get the left motor value that we're going to use to set the PWM value through the drive routine coming out the L293D to control the speed of this motor. So left motor says how fast this motor is going. 255 means forward, minus 255 means backwards. So if it's greater than 0, we're moving forward. And LED 0, the 0th LED in our segment, we're going to use the set RGB function to set it to 0 for red. Left motor divided by 8, okay, because we could just leave it at left motor, but that would take it all the way up to 255, which is really bright and consumes a lot of current. We don't necessarily want that. And 0 in the blue. So you could pick a different color there if you wanted, and you could pick a different brightness level too. 255 divided by 8 is roughly 32. Okay, and so we put that in there, and then you can test that and compile it and upload it, and you can drive forwards and backwards. And it should go off when you're going backwards, but it should go nice and green when you're moving forward. Now, we can take that line again and just make sure I didn't, two screens here. You don't see the second screen. And if I move my cursor over there and I hit the space bar, my mistake, I hit pause, and then I get to go back and reshoot that part of the video. So anyways, I just took this part and copied it again. Now you'll notice it says, well, if the left motor is less than 0, which means I'm moving backwards, okay, now I want it to turn red. Okay, so in my red, green, blue, those 3 different colors in here, so this little section right in here, I've got ABS left motor divided by 8. Now the ABS just means absolute value, okay? And so absolute value means if there is a negative sign, throw it out and give me the positive value. Okay, so if it's less than 255, and we know it's going to be, okay, because otherwise we wouldn't execute this if statement. We've got left motors less than 255, so say it's minus 128 comes in here, it runs the ABS function on that. It says, oh, minus 128, just get rid of the minus, it becomes 128, divides it by 8, and that gives us our value, and it puts it into the red value right here, so it goes red depending on our motor's reverse speed, and both of those would control the 0th pixel on there. Now, to have the right motor control some settings, then I come in here and I use the same commands. I just copy and paste them down, and I change from left motor to right motor and left motor to right motor right in here, and from LED 0 to LED 7, because even though it's the 8th LED in a row, we started counting at 0. So 0, 1, 2, 3, 4, 5, 6, 7 is 8. Okay, so now that gives us control over the colors of the LEDs on there. And when I go ahead and hook my robot up to the phone, I should be able to see those colors change. Connect to the Boombot here, and if you've got that code on your machine and running, you should be able to hook up to RemoteXY over your Boombot, and there we go, forwards and backwards. Forwards, the LEDs come on green. Backwards, they turn red, and they never get all that bright. Yes, we've got that data coming through right on here, and we can see that as well. But it's just another way to look at it, and it moves the blinky up to the front of the robot so it's easy to see. And it's kind of cool because you're controlling the brightness from your phone. And don't ask about this. Okay, well, since I mentioned on there, I'll talk more about that setting later on. You can come along, and on your phone, you've got a whole selection of things for controlling RGB and brightness. And that'll be included in a bonus section later on at the end of the video, which I recorded a little while ago, and we're putting all together with editing. Anyway, never mind all that. I also wanted to do the inside buttons here. You can see I've got one in red right here, and that one is actually hooked up to the edge detector. So when I lift it up, you can see it. Well, maybe you can't see it. It's hard to see. Camera is having a really hard time with these super bright little LEDs, but it switches it over to blue when I go backwards, and depending on where I am relative to the black line, it gives me the answer right in there. So this is how I went about setting that up. Okay, you'll recall when we did our reading of the right edge and the left edge detectors, we used the command analog read brackets left edge. Now, if you put this code exactly into your program, you may run into an error because left edge, right edge, and black line may not be defined right now. You may have to go back to your edge detector program, and hopefully you've been saving this at every step you go along with a different code, or with a different file name. And if you go back to that, you'll be able to find the values that you had set in there for left edge, right edge, and for your reading of a black line from doing your line following, okay? And all we do in here is we're coming along and we're saying, well, if our left edge is greater than that value for the black line, then we're going to set the LED number 1. So this is the 0th one on the edge, so we're going to set LED number 1. We're going to use the set RGB function to nothing red, nothing green. We're going to set it to blue, okay? And we're using the map function. And if you've used map before, you know it's a really handy function. If you haven't used it before, you can access more information about it by highlighting it and going find in reference. And your help file will pop right up on there. And basically what it tells you is that you're going to put a value in. So in this case, we're going to do an analog read, and we're going to get a value that's somewhere between 0 and 1024. Okay. And then it is going to take that value and it's going to take a look and it's going to say, well, from low. Okay, so it's going to say, I'm going to put that value somewhere in the line from a low of 200 to a high of 1024. Okay, and then I'm going to map those values to a different set of values over here. Okay, and those values are going to go in this case from 0 to 32. And I just chose 32 because 32 is a nice binary brightness level for our Neopixels. We seem to be using that. You can still see gradations of brightness up to about 32, and after that, it's just really, really bright on your eyes, especially indoors. So what we're going to do is we want a number between 0 and 32. And we're going to read a value, we're going to drop it in there. And so if that value's it's going to plot it right in between here. It's going to say, where does it land in here? And then it's going to plot it out to those values over there. So as it starts to go higher, this gets brighter. As it starts to go lower, this gets dimmer, and it scales it out. You could do the math mathematically, but this just maps it out really nicely for you. Now, if the value is less than the black line, which means you're over a white line, I don't know why I had to think about that. Then what you've got is you're going to read your left edge and you're going to map it from 0 up to the black line. So the black line is the highest possible value that you could get, because we know now that it is the analog read has to be less than the black line value. And it's going to map that somewhere in the 0 to 32 range again, except this one's going to be mapped into the what color have we got in here? This one's getting mapped into the red. Okay, and there's the green and there's the blue values right there. And we can do that for the other side as well. There we go. And now you've got inputs on both sides. So as I flip that up and down, you can see that these LEDs on the outside are changing. And remember to check your code every now and then as you go through and do it. So that is what I've got in the update LEDs. And never forget that if you actually do want them to update, you've got to put fastled.show in there. Now there's a little bonus section to the video where I talk about how to add that neat little, oh, I've lost connection here. That neat little dial right on there for controlling your RGB values. Okay, and if I bring this down right over here, you can see when I hold this on here that I can spin this dial around. And as I do it, there we go. I get different colors coming through on those middle ones. And as I play around with that, I get different brightnesses coming on there. Yeah, that's what they look like when they're full brightness. Really kind of difficult for the camera to pick up. So that code, and I'll talk more about it, is not that code right there. And it actually works pretty good, but there's a few other things that you have to do. So hang on for the bonus section of the video where I show that to you. Okay, back here, and this is the bonus portion of the video, kind of like right at the end of a Marvel movie where they roll the extra credits on here, except I'm not telling you about the sequel that's coming up. I'm telling you that I thought it was really cruel to say that you could put an RGB thing into your RemoteXY code and not give you a little bit of a hand on how to go about doing that. So I've come into RemoteXY and I've completely rebuilt my screen, and now I'm like, how do I fit that into code that I've already got? Okay, because there are 1 or 2 glitches that you could run into. So I'll walk you through how I'm doing it. First of all, remember that in your configuration, we can set the screen up however we want with these doodads from over here, but we've got our Wi-Fi access point, our Arduino Uno, ESP8266 module, and our Arduino IDE. If you're using a Bluetooth module, you can set it up right in here too. It works great. Our connection interface is going to be the hardware serial, and lo and behold, we can leave it sitting at 9600 bits per second now because well, we're running at 9600 bits per second. We've changed the speed on our ESP8266 so that it works at 9600 bits per second. So this should be good. And Wi-Fi access point, create your name. You can have a password if you want. I've made it open, and I've played around with my background color. Anyway, you can watch the other video for all the different things that you can do in here. I've just added one more element. And now I'm going to get my source code right here. And I'm going to shrink that window a little bit so that I can copy some of that source code into my Arduino code. And I want to be able to share that screen without them all hogging everything. So I think now you can see both screens. Okay, now you'll recall that in here we did all of our setup for RemoteXY right in here, and most of this stuff will be the same, okay? So RemoteXY connection settings, that section and this section are identical. I don't think they've changed. We got 9600, Boombot, No password. The port is 6300. Okay, now we do have to change right in here. So this Pragma pack push is the same, but you can see this is a larger configuration variables right in here because we've got more elements that appear on the screen. So I need to copy that section of code out of there and replace this section of code right in here. Okay, and just do a verification right now and make sure that you've done that okay. Okay, that worked out pretty good. Now, RemoteXY inside its structure right here. Okay, here's that struct right in here. It's got some input variables. uint8t joystick 1x is still the same. uint8t joystick 1y is still the same. And this one right here, because I rebuilt it in my first one, that showed up as button 2. In here, it's going to show up as button 1. All right, so I just need to take that, and I am going to have to change that code elsewhere in my program. So I'm going to copy that, and this is my fire button right in here. Okay. Okay, now because I got rid of button 2, let me just do a find in here. Okay, let me look for button underscore 2. And anywhere I've got button underscore 2, I'm going to replace it with button underscore 1. Okay, and let's just do a replace and find, and it takes me through there. So oh, that's a different setup right in there. Where are we here? There it was. Button 2 just got replaced with button 1. And I think that was the only place I can hear it telling me that it's all done. So we can come back up to the beginning of the program. And so because I changed that one variable, then let's see right on here. Now we've got 3 new variables that came right through here, an R, a G, and a B. So we are going to copy them. And we're going to put them into right here. And now that I think about it, I'm just going to keep everything in the same order. So before button 2 was up there, I'm going to cut that out right there. So this is joystick 1X, joystick 1Y, RGB, and then right in here, it's got button 1. I added a second value to my graph in here because I thought I might want to plot something later on. Right now, I'm just plotting the voltage, but can put more than one thing on the graph. Okay, online graph. Oh, and it also changed the names because I've got multiple variables on here. So I'm going to get rid of online graph 1. Okay, notice, see, I'm getting rid of online graph 1. Let me just put that right in there. Tools. So this is the one I'm getting rid of. I want to make sure that nowhere in the code do I have just online graph 1. Now, if I go and do a search and destroy on it completely, then it's going to work on these 2 right in here. I need to be a little more careful. I need to just do a find this time. Okay, find online graph 1. Okay, so find, and I'm going to change it to online graph underscore var 1 right now. Okay, so I didn't want to change those 2. It's right here. I want to change that to var 1. I'm not quite sure what I'm going to do with online graph variable 2, but I figured I'd put that in right now. And I'll just do a check and make sure that's all compiling okay. Done compiling. And now right up here, online graph var1, online graph var2, uint connect flag, and that looks good. So now I've been able to take this information, copy the new stuff in, paying attention to the rest of my code to make sure that if I changed a name up here, I changed the name in the rest of the code. And now I can come over to my update LEDs, okay? And in the update LEDs section, I can say LEDs. Let's see, we've done 0, we've done 1. So I'm going to start at LED 2 on here. LEDs 2 dot set RGB, okay? And then we just come in here and it will be, just make sure we use the name correctly. So this is going to be RemoteXY dot, okay? So this structure in here is called RemoteXY. So RemoteXY dot RGB underscore 1 underscore R, okay, comma, remote XY dot RGB underscore 1 underscore G, okay, comma, remote XY dot RGB underscore 1 underscore B, brackets, semicolon. And let's see if that compiles properly for me. Normally I've got the code all worked out in advance. This time I'm just throwing it together. Like I say, little bonus material because I tempted you with the ability to control all this. And let's make it so that we can control all of those ones in the middle this exact same way. I'm just going to copy that code and put it in here. And so do that a couple of times. And now we'll set LEDs 2, 3, 4, and 5. So we'll control all of those 4 in the middle with our little controller on the board. Update that. Hey, it all compiled. It worked. I hope you saved your old code. It's always good to save your old code before you go and confidently updating things that don't work, because it's nice to have the old one to fall back on. I didn't do a very good job of demonstrating that, but trust me, I've got it saved away somewhere on here. And now I can connect to my Boombot. And run RemoteXY. And now my screen looks different. Okay, see, I've got that RGB controller on there. And if I start sliding that around, that's working. Oh no, what's up with my RGB controller? Oh, there we go. I just need to get my thumb on there. And oh, the inner circle controls the brightness, and the outer circle seems to control the hue. Oh, that's really bright. Dim that down a little bit. Brightness and hue. There we go. So now you can slide those little sliders around the outside and you can control the color of your LEDs in real time as you drive your robot around. Have some fun with that. All sorts of stuff you can do. As I say, if you can blink an LED, you can rule the world. Some assembly required, batteries not included, instructions available in a language that you don't understand. Have a good afternoon and enjoy your Boombot.